Hi everyone, I'm Ben Amneshabur. I'm going to talk about the PAC-Bayesian approach to generalization in deep learning. This is a joint work with Srinath Bhajanapalli, David McAllister, and Natis Rebro. Okay, so I've been working on generalization in deep learning for maybe like 2 years, and I've tried, I started from reading about Rademacher complexity and then reading about covering numbers and all other stuff, and unfortunately just recently moving to PAC-Base, and what I understand from PAC-Base is that it somehow simplifies everything in calculating generalization bounds in deep learning and any complex system, at least based on like small observations I've made. So I want to share it with you, and I'm hoping that you continue to work on this and increase our understanding of generalization in deep learning models. So, so we know neural networks are over-parameterized. In many settings, we have more parameters than number of data points, and that means we have too many global minima. We have too many points that we have zero training error, and some of them generalize well, and we know some of them don't generalize. But somehow SGD or optimization algorithms we use find the ones that generalize. So what's going on here? Why is it the case that the optimization algorithm we choose ends up at picking the right one? The only explanation one could come up with is that these optimization algorithms are biasing toward a solution with low complexity, and this low complexity is the one that we don't understand. How can we find a complexity measure for neural nets that correspond to what is happening in practice? So what we expect from such a complexity measure, so let's say W is the parameter vector and R of W is the complexity measure we are talking about. For example, it could be L2 norm. What we really want from such a measure is that a set of neural net with complexity measure has a small capacity. So we want to prove that it has generalization. And we want to also be able to say that all natural problems that we're interested in can be expressed by this class. And the last thing is that because we hypothesize these optimization algorithms are picking solutions from this set, we want to show that these optimizations are biasing towards solutions in this set. So in this talk, I'm going to talk about the connections to margin, get some margin bounds using PAC-Base, and then discuss some connections to sharpness. And at the end, I'm going to look at 3 empirical observations in deep learning that has done by some people, and discuss whether PAC-Base can tell us something about these phenomena. One of them is that we can feed random labels by just doing SGD on deep networks, and same algorithm can also generalize on other data. So what's going on here? And another one is that different optimization algorithms end up at different global optima, and they have different generalization properties. Can these generalization bounds tell us which one of these global optima generalize better? And the last one is that larger networks generalize better in some settings without any regularization, so just running SGD or gradient descent on neural networks, and larger network gives better generalization. Just some notation. For simplicity, we are just looking at feed-forward nets with D layer, and we assume all layers have H hidden units and ReLU activations, and B is the bound on L2 norm of the samples. And I'm using this margin loss, which is probability of the score of the true label minus score of other labels being less than gamma. So that based on this definition, L of 0 is just misclassification. So one way to look at capacity control is just size, number of parameters, but in all of those observations that I told you, there's no way this can explain it, because in 2 of them, the size is always fixed, and the third one, we observe that this increase in size gives better generalization, which is opposite of what this capacity control suggests. So we should be looking for something that depends on the weights rather than size of parameters, and then we get to scale-sensitive capacity control. And here we have to look at the scale of the weights and also the scale of the predictions at the same time. Because I can always scale up the weights and it looks like I'm getting a better margin and I'm separating the data better by just multiplying the weights, but that's not true. So I have to kind of measure how much I'm separating the data divided by the weights, and that would give me something meaningful. So for margin, I'm defining the margin as the score of the correct label minus the score of other labels. So let's say this is the margin, and now we are looking at different norms. Like these are generalization bounds that are proved before using different methods. For example, L2 norm is just, I'm referring to it as L2 norm, but it's product of Frobenius norm of the layers divided by the margin. And as you can see, these units cancel out. And if you just scale the weights by some number, then the margin would increase and these two cancel out. So you can do like some tricks like this. And another one is L1 path norm, which is the generalization bound is just same as done by Bartlett. This is just optimizing the weights by rescaling hidden units. So I don't go to details of definition of two path norms. And the newer bound, which is really exciting and interesting work by Bartlett and others, is something that depends on the spectral norm, and that says the capacity is product of the spectral norms divided by the margin times another factor, which is L1 of the weights divided by a spectral norm. And you can see, like, I have the definitions down there. Okay, yeah. So these are the definitions. So this is this was presented as a spotlight here, and when this was on archive, by the way, I forgot. So they recently improved it in maybe like 4 or 5 days ago to this group norm, which is taking L2 norm of incoming weights to hidden units, and then taking L1 norm on top of hidden units. So when I looked at this bound, this is proved with covering number, and back then I was just reading about PAC-Bayesian and working with David, and I realized this, like, it was a rather involved proof. I realized there is a much simpler way, like using the same intuition, there's a much simpler way to prove it with PAC-Bayes. And now that's what I'm trying to do here. So I'm using this theorem on PAC-Bayes, which is not tight, but it's kind of giving me what I want, just to show that, like, how simple it is to get a bound. So this one says the loss on the posterior can be bound on the distribution can be bounded by the loss of posterior training set plus the KL term divided by number of training samples, roughly. So, but in many settings in deep learning, like, okay, we are doing SGD, but we also get generalization with gradient descent. So I'm just separating the random behavior of the learning algorithm, and I want to know if I have a fixed W. So let's say I run gradient descent, so it's a deterministic algorithm, I have a fixed W, I want to know how to use PAC-Bayes to get the generalization path. So the way we can do it is by assuming a distribution over W plus U, and U is acting like a random perturbation. So that would define the distribution over solutions. And now I want to see if I can get a generalization bound similar to one that I showed you by Bartlett using some distribution like this. So now I have defined my distribution over the noise instead of the parameter, the final parameter that I learned. And what I want to do is that I want to know what is the bound for this. So looking at this, this is just saying how much the loss would change if I perturb parameters, right? And this roughly corresponds to the margin. If I have large margin, that means that if I change the parameters a little bit, it's not going to change the loss. And that's the intuition that I want to use. So this lemma is just something that's out there in many PAC-Bayes papers. This is like shown for linear classifiers. So I'm just rewriting everything. And this is saying roughly that if you perturb things from perturb parameters by U from distribution Q, and with high probability the output function is not changing much, then you get this loss, which is margin loss plus KL. So it's basically saying, make sure that your perturbation is not changing the function by more than margin, and then I'm bounding the loss on the expected loss by this margin loss, and I get KL. So this is like, has shown for similar results for linear predictors.
Excuse me. The KL divergence, you need two distribution here.
Yeah, so I'm a little bit abusing the notation. So W plus U is a random variable. So U is a random variable generated from some distribution, and W is fixed, so it's centralized around W.
So it's a distribution centered on W.
Exactly. Yeah, so we want to know how much the network output would change if we perturb the parameters. And this is what we get. So it's very simple, actually. All you want is a local Lipschitz property of neural networks, and that means you want to know if you perturb the parameters, how much the function would change, and of course that's the Lipschitz of the network. So the intuition is that you can just write this Taylor expansion, and the gradients would, at this point is bounded by product of spectral norms of the weights, because we are using ReLU. ReLU has Lipschitz constant 1, so everything is straightforward. It's just like 5 lines.
I'm sorry, I have a question about the notation. B is the upper bound on X, right?
Yeah. And then when you have the bound on this thing, you can ask, if I pick U from Gaussian, what should be the variance so that I make sure this change in the function is not large, and substitute it in KL. And then you get the generalization. So the whole proof is like 1 page. And this is the bound. So the bound says product of spectral norm divided by this. So now let's do some experiments, and let's be done with theorems and see how it works. So this experiment is in untrue and random labels, and we want to observe that these measures are higher on random labels, which shows that they can capture complexity of neural networks. And we want to also see that these measures increase almost linearly with the size of the training set when you're learning random labels, because it should memorize everything, but it shouldn't increase as much on true labels. So as you can see, all of them, I'm plotting all of them. The last one is the one that was suggested by Bartlett, and also you can get something very similar with PAC-Bayes. But you can see all of them can actually tell you which network is learned on random labels, which is like something you expect any sensible measure to be able to do. So it tells us that SGD is kind of picking the neural net with low norm. There was also sharpness that was suggested by Keskar. So they observed that the change in the loss is much more when you perturb parameters if you train with large batch size. So the intuition is flat minimized better, and then they suggested maybe sharpness is something that captures this generalization behavior. But similar to margin, if you just look at the sharpness, it's meaningless because you can scale up the weights and you get better sharpness. So if you just look at the sharpness based on that definition, you see that actually it's the opposite. So the ones trained on random labels have low sharpness. But in fact, Dan is going to talk about this, and in this work, sharpness, they showed that sharpness can be understood as one of the 2 terms in PAC-Bayes. It's very interesting, and I invite you to follow that, and there's also another work that Dan's going to discuss. But roughly, so the intuition is that you can decompose this expected loss to actual loss plus expected minus actual loss that you care about. And now this would be expected sharpness, how much the loss is changing by perturbation. And the second one is the KL term, so I just assume everything is Gaussian, and it gives me L2 norm. Now I plot, so because the exact way we prove things changes the way these 2 measures correspond to each other, he suggested using bicaretary plot, which we plot expected sharpness versus KL. And what we expect is that if we fix one of them, so if I fix expected sharpness, the KL should increase for random labels, should be much higher. And you can in fact see that the KL is much higher for random labels compared to true labels, and also it's changing much faster. Second experiment was with global optima. I want to generate several global optima, and I want to see if these measures can tell me which one is going to generalize better. Because that would be very good, because you can then design optimization algorithms using these measures to find a better global optima. The way we do it is that we have this optimization algorithm that takes a training set, and then it has this confusion set inside it, which has some data with random labels. So it minimizes the loss on training, loss confusion set, and the final solution is going to be global optima for the training set, because it found the 0 error on training set and 0 error on confusion set. And then by changing the size of confusion set, you get worse and worse global optima. So we actually plot these measures versus the test error. So all of these points are global optima, and each of them have different test error. And you can see that all these norm-based measures can capture this. And this is also true for expected sharpness and KL, which is by PAC-based bound. You can see if I fix sharpness, the one that has higher test error is going to have higher KL. And the last experiment is increasing network size. So the observation we made was that when you start training, so for each of these experiments, I train a network with different number of hidden units using gradient descent. This is with SGD actually, but I've tried gradient descent, conjugate gradient, so it's not an SGD property. And you can see that the training and test error goes down to some point, and then at 64 is enough at this point to get zero training error. So I expect the test error to go up and overfit. But what actually happens is this, without any regularization, without dropouts, and anything else. So we expect these measures to be able to capture this. But none of them can actually exactly tell us what's happening. So this plot shows the number of hidden units versus the measure. Sharpness and spectral cannot capture this well. And path norm and L2 norm are partly capturing up to 128, but later they also explode. And this is also true with KL. So KL can tell us 128 units is better than 32, but not with higher ones. So yeah, so this is still something we have to work on. So what we learned is that PAC-Bayesian approach can give us margin bounds for neural networks, and it's much simpler than other ways you can use, at least until now. And also, PAC-Bayesian theory can capture some of the generalization behaviors we observe in practice. And I want to end with this question, and that I'm trying to a little bit answer in the next slide, is how do we use this in practice? And because optimization is tied to geometry, we might be able to use some of these intuitions, because you can think of a steepest descent approach, which is basically improving the loss as much as possible, but subject to a small change in the model. So we don't want to change the model significantly in each iteration. And this small change should be captured by measure, by distance measure. And distance measures give you different algorithms. For example, gradient descent is the steepest descent with respect to L2, coordinate is the steepest descent with respect to L1, and we have also suggested path SGD, which is the steepest descent with path L2 norm, which is like more appropriate for neural networks. And this is also something that I think that Dan is gonna talk about like optimizing prior, right? Yeah, so optimizing prior, which is connecting to PAC-based. So I think these are very exciting areas to work on, and if you have any questions, I'll be happy to answer.
Thank you very much, Ben, for this very nice talk. We have time for one quick question.
So if with these bounds you can explain all the empirical behavior of these methods, would that be like a full resolution of the generalization behavior, or do you want to kind of also explain why gradient descent would find these type of solutions?
So part of the question is why it finds part of these solutions, but when you find this measure, there is opportunity to actually design optimization algorithms that directly minimize this measure. It could be the case that SGD is indirectly affecting this measure, but not actually optimizing it. So the hope is to be able to actually optimize these measures.
Okay, thank you very much. Let's thank Ben and all the speakers. So we now have our lunch break, and the next talk will begin at 2.